thank you all for coming today. We are very privileged and excited to have with us Professor Sang-Yoon Chang, and he is an associate professor at the Computer Science Department at the University of Colorado at Colorado Springs. I'm going to read some of this just because it's kind of technical, so I'm not, I wouldn't want to put it in my own words and get it wrong. He received his BS and his PhD from the Department of Electrical and Computer Engineering at the University of Illinois at Urbana-Champaign in 2007 and 2013. Dr. Chang is the head of the Networked Systems Security Lab at UCCS, at the University of Colorado, and his research interests lie in the security of networked systems, particularly in the areas of wireless mobile, cyber physical, and distributed systems. So it's super important and topical. His research has been funded by the NSF, ETRI, Colorado State, and CRDF Global. And at the University of Colorado, Dr. Chang is the director of the PhD in Cybersecurity degree program and the lead PI and director of the Cyber Core Scholarship for Service program. Outside of the University of Colorado, Dr. Chang offers a MOOC course in applied cryptography through Coursera. He is also a board member and executive team member at the Silicon Valley Cybersecurity Institute, a nonprofit organization for cybersecurity research, education, and training. So this could not be more topical and important, and we are super fortunate to have somebody who is very knowledgeable and right at the center of research on these topics. And so with that having been said, let me turn things over to Professor Chang to tell us about secure machine communications from AI sensing to machine learning to post-quantum cryptography.
Thank you for that kind introduction, Dr. Lucas. So yes, I'll be talking about securing machine communications from AI sensing to machine learning to post-quantum crypto. The second title of this presentation is the overview of the research that we do at the Network Systems Security Lab. So I will be sharing some of the results that we have, the R&D results that we have. But I would stay at a relatively high level so that it also overlaps with some of the trends in AI and cybersecurity. So I do want to strike that balance. It's my pleasure to speak here, at the World Affairs Council of Tacoma. So thank you for having me. Okay, so as introduced, I'm Sang-Yoon Chang. I also go by Sang for short. I work in the computer science department at University of Colorado Springs. I'm an associate professor there. And I was hired as a cybersecurity faculty. So I work in cybersecurity at UCCS and outside of UCCS. Probably a couple things that are related maybe to this presentation is that I do direct the Cyber Core Scholarship for Service, the SFS program at UCCS. And this is actually a collaborative work with University of Washington Tacoma. The PI from Washington Tacoma is Dr. Yan Bai. And Dr. Bai was the one who actually made this introduction, for me to present today. I'm also working in this nonprofit organization called Silicon Valley Cybersecurity Institute, or SVCSI. And earlier, I was talking with Dr. Lucas about the nonprofit and the member composition, and I was just trying to get a feel about, the nonprofit organization with WACT. I did want to start by sharing my research interest, and they span across system security, applied cryptography, computer networking, and wireless communication. I actually started off as a person working in wireless communication. So that's the circle on the right bottom corner. And I was a signal processing person back in my bachelor years. But then I started moving more toward, left and upper corner. And now I'm hired as a system security or cybersecurity person. By training, I was an EC major, but now I work in the computer science department. Okay, so I have this slide, and it's titled Presentation Overview. And I wanted to start by talking about the key topics or the subjects of this presentation. they do have a unified goal, and the unified goal is to secure machine communications and networking. But I'll talk about how AI sensing, machine learning, and post-quantum cryptography within that context of machine communications. Now, when people talk about I think many people here these days, think of information which are encoded in images or natural languages, such as English. But um, this presentation will actually expand beyond that in terms of the information that is being shared and being communicated. We will actually see those information which are more related to the EM, electromagnetic signals, or the bit streams in networking packets. So I was invited to give this presentation, and I was invited to speak about AI and cybersecurity. So I thought about like how I would like to actually gather these topics. And that reminded me of this show called Silicon Valley. It's an HBO show. It's pretty funny. It's a sitcom. But here I'm showing the posters of season 4, 5, 6. So these are the three last seasons of that HBO show, Silicon Valley. And the reason why I'm showing you this is because each of these seasons, they do talk about these engineering technologies. So season 4 and season 5 were about blockchain, cryptocurrency, decentralized peer-to-peer internet. And then season 6, focused on AI and how that AI broke the encryption that we currently use. And because of that, Richard and the company Piper, they actually failed their launch intentionally because they didn't want to have that AI, which can break the modern day crypto. And these topics are very related to topics that I'll actually cover in this presentation. If you look at these posters, then the posters for each of these seasons, season 4, 5, 6, these are intentional. These are by design. So the loading sign in season 5, that is the poster of season 5. And the big fonts for season 6, the small font there reads, "How big is too big?" That's also intentional. And they end up just failing their launch and deciding that they'll actually just that they'll contain the AI engine that they have because they wanted to protect the modern day digital systems, which are protected by cryptography. I will come back to this slide because this is like the slide that actually it's the presentation organization slide. So I'll try to come back. And let's start by talking about these two topics, AI sensing and machine learning. Some time ago, precisely more than a decade ago, I was working on my PhD. And during my PhD, I was working on wireless communication, security, and availability. More specifically, we were working on building intelligence, on these radio control, which were called cognitive radio or intelligent radio. And so cognitive radio is a technical term. Now, but then we still had that control decision, sensing to gather the information, and based on that sensing, we make intelligent decision for control communication, and then using that control communication to set up data communication, and then use the feedback to continue to learn about the environment and about our control to make better decisions in the future. So I didn't use the term machine learning back then, but we were using machine learning, and probably one of the more closely related concepts in machine learning is reinforcement learning that we used. So there was a sense of processing or intelligence building, and there are some actions that were taken based on that intelligence. And then there's a reward or some type of feedback that we can use to make more intelligent decision moving forward. Okay, so let's talk about sensing and machine learning. This presentation does focus on securing network systems, including mobile and distributed networking. So think about 4G, 5G cellular networking. Distributed networking will actually talk about Bitcoin and cryptocurrency. Um, if you consider I do consider AI to be a little bit broader term than machine learning. So machine learning is about given the information, processing the information, and deriving insights or intelligence. Whereas AI includes that machine learning, data processing, but it extends it to include sensing and data collection. And these two parts of AI are very much related to each other. So we have the sensing and data collection, and that informs the data processing in machine learning. And of course, based on the machine learning, that can actually inform us to take different actions or sense differently. So we do have a feedback between AI sensing and machine learning based data processing. And the context that we'll focus on is 4G, 5G cellular networking, the mobile phones that we use to connect, as well as cryptocurrency, more specifically Bitcoin, which is the most popular cryptocurrency out there. So why is sensing and data collection important? Because there's a lot of people within the discipline of computer science that takes machine learning and do data processing. Um, there is a little bit less people who actually implement the prototype, implement the sensing, and collect the data. So I did want to highlight, or address why sensing, prototype implementation, and data collection are important. And the reason why it's important is because it directly affects the effectiveness and the accuracy of data of machine learning, data processing. It's also very related to the systems thinking and approach because we want to think about what is important in that system problem. And based on that, we want to build and design the AI, including the machine learning. So to highlight or to better address this importance, let's raise two questions. So are the data appropriate for the AI goal? And that's directly related to the type of information or data that we're collecting and sensing. I have a figure here on the left bottom corner. If you're not given the entire system, or if you don't understand the entire system, then an elephant can be perceived as a carpet, snake, or rope, depending on, which side of that elephant you're viewing or you're sensing. Another question that addresses the importance of sensing and data collection is how reliable and accurate is the data? Can we ensure its integrity? So we know that with ChatGPT, Copilot, and all these LLMs, large language model applications that we have, those are based on the information that is currently out there on the internet. So this kind of reminds me of my earlier years when I was told not to cite Wikipedia. Now, Wikipedia oftentimes provides good information. Um, Almost always it does, but then it's crowdsourced, and therefore, it does in some of the critical cases, it does lack the accuracy that we actually pursue in science. Another related example for this is when I was growing up, and I'm from South Korea, born and raised. I was told that turning on the fan, when you go to sleep, is bad for your health. And we all know that is a misinformation. And I think but I used to kind of believe in that, when I was really young. But um, knowing what information to sense, knowing what information or data to collect is very important for AI and machine learning. Okay, so let's talk about Bitcoin cryptocurrency. Um, and I'm going to talk about three different problems within that Bitcoin and cryptocurrency. We do have a prototype in Bitcoin, and this is an active Bitcoin prototype. So we actually just inherit the Bitcoin core code implementation, but we just add passive measurements. So active functionalities are all Bitcoin, but we just add, more information collection, sensing, and data dumping, on top of it. Now, this prototype, by building on the active Bitcoin node, it actually enables us to draw data that is beyond just the Bitcoin ledger data. Um, and this is just from my experience that when many people talk about Bitcoin research and development, and when they talk about data, it's oftentimes the ledger data. So the ledger data that we actually download when we first implement Bitcoin. Um, but we're actually trying to look at a different layer, including the underlying peer-to-peer networking layer, so that we can actually better study, so in a sense, we're trying to collect more information. Um, we also try to study the interplay between the consensus protocol and the underlying peer-to-peer networking. So this is important because the consensus protocol is how we can agree on. It's a very democratic way um, to agree on which transactions we should process. And this probably makes it easier if we can assume a centralized environment. If we have a centralized authority who can just say, these are the transactions that we process. But in Bitcoin, there are a couple challenges. One is that we try to do this in a distributed manner. The other issue is that we try to skip registration control. So it's called permissionless. And this is how Bitcoin got invented. It started at the cypherpunk community, and they really focused on anonymity, and they wanted to do it without needing to register. And their rationale was that if we have an authority that controls who can participate versus not participate, then that itself can be a vulnerability against having that distributed processing. Um, but our prototype, we actually have, information sensing on the peer-to-peer networking layer as well as the consensus protocol. And of course, the peer-to-peer networking layer is very important because it actually delivers these critical parameters, including the newest block and the newest transactions, which are the inputs to these consensus protocol called proof of work. Okay, so let's talk about anomaly detection. These peer-to-peer networking, um, blockchain cryptocurrency is a very good application, and I think the market cap is huge. But people actually are trying to envision the use of the blockchain beyond just the cryptocurrency. So going back to Silicon Valley, that's why they're thinking about decentralized web, the next generation internet, decentralized peer-to-peer, networking. Um, but I think we do focus on the Bitcoin cryptocurrency. And for this implementation, in addition to collecting normal data, we do simulate attacker behaviors, Eclipse and DOS attack. DOS is denial of service, as well as some non-security related anomalies. So including the Bitcoin halving event. So Bitcoin um, actually lowers the newer currency that gets introduced or the minor setup change. And we actually try to process these data for anomaly detection using machine learning as well as statistical, more classical approaches. And we actually see that we can detect the anomaly. And going back to the interplay between the consensus protocol and the networking, we actually show the overheads of such anomaly detection. So we actually look at how it affects the hash rate. Um, Now, earlier I mentioned about peer-to-peer networking and distributed peer-to-peer networking. It has this characteristic of supporting um, like a diverse set of peers. And when I say diverse, I'm talking about peers who may be stable in terms of their connectivity versus those who may not be. So if a peer disappears or a node disappears and it gets reconnected, then the distributed networking is meant to support that. Um, because of that reason, we also estimate the connectivity of that we have given the set of peers that we're currently connected. So on the bottom left, we actually show like how the arrivals of these different blocks, how they affect the scoring mechanism that we have to score the connectivity level that we currently have with the connections that we currently have. And then, for each of the block arrivals as well as transaction arrivals, the score increases because the more the peer deliver, the set of peers deliver these critical information, the higher we rate our current connectivity. Okay, so let's talk about network fingerprinting, and this goes back to the background in Bitcoin cryptocurrency, talking about anonymity and permissionless requirement. I mentioned about cypherpunk community, and they really want to have these financial transactions that can skip censorship. So anonymity is one of the key requirements of Bitcoin cryptocurrency. It is also one of the characteristics and requirement that makes the Bitcoin cryptocurrency more complex. Um, and this actually, as a researcher, this actually makes Bitcoin and these permissionless blockchain to be more interesting than some of the other blockchain um, applications, including those that are permissioned or consortium blockchains. Um, Now, because of that reason, the Bitcoin, including the Satoshi Nakamoto paper in 2008 and 2009, they actually do have a strong protection of anonymity at the application layer. So that's at the application and the consensus layer. But at the networking layer, they largely build on the existing techniques. And one popular existing technique is this technology called Tor, the onion routing. So the onion routing introduces, these arbitrary relays between the source and the destination so that the packet does not get directly forwarded to the destination, but it bounces off on these relays. And that way, we can have the anonymity protection on the networking layer in addition to the upper layers, including the application and the consensus. And this makes sense because we don't want to have anonymity compromised in one layer, and that will compromise the rest of the layers. Um, so we collect data using non-anonymous routing, so that's direct IP, but then we also collect anonymous routing by the anonymity routing protocols that are supported by Bitcoin Core. So these are the existing anonymous routing protocol that is supported by Bitcoin. At the time of our experimentation, the Bitcoin Core supported Tor I2P and CJDNS, and all of these are anonymous routing protocols. But we actually found that nobody was using CJDNS, so nobody was generating traffic on CJDNS. So that's why we focus on Tor and I2P. But we actually investigated that. And what that triggered us to do is to use the networking behavior to fingerprint the networking traffic so that we can detect if the traffic is indeed using anonymous routing or not. And this is to detect or defend against false claims because not using anonymous routing has lower latency because you can directly connect or directly send the packets to the destination. Okay, so this is one of the backup the book tap slides, and now I want to shift gears and talk about 4G 5G cellular network. And this sticker that I have on the right corner is actually something that is called software-defined radio. Um, yeah, and I'll talk about that in the next slide, but I'll talk about like threat detection, DOS, and the fake base station. So we do use this software-defined radio or SDR, and this is really important when we think about the security for mobile computing. So earlier I mentioned that I used to be communication signal processing person going back to my bachelor years. Um, Back then, when we wanted to do radio R&D, it was mostly based on hardware. So I remember TAing like a communications lab, and it was very hardware based. Now, software defined radio, software defined actually provides the capability for controlling the radio functionalities, including which frequency to transmit by using software and using code. So it actually really expands the customer or the users who can start doing radio R&D to computer science. This coupled with some of the open source softwares that we're seeing in the 4G, 5G community, including SRS-RAN and Open5GS, these are actually really facilitating the R&D in the cellular networking context. Now, this is a little bit in contrast, or it's a little bit late compared to Wi-Fi or 802.11, because Wi-Fi and 802.11 operate on unlicensed band, whereas these 4G, 5G cellular networking operates on licensed band. So there's a critical difference there in terms of how those actually affect um, how Wi-Fi got started, the R&D got started way quicker than the cellular networking, because we used to have, a lot of R&Ds and Wi-Fi, and some of the open source kind of resources so that just common researchers like myself, can use them. But in the proprietary and licensed band operations, it was a little bit harder to work there. So while even though cellular networking and Wi-Fi may look similar from a consumer perspective, there is a critical difference in terms of Wi-Fi starting the open source earlier and therefore facilitating greater R&D in cybersecurity earlier than cellular networking or 4G, 5G. We're going to talk about two different scenarios. Like on the bottom half, I have these diagrams, um, and it just captures, some of the key architectural entities in cellular networking. So on the far left, we have the user equipment, which is the beneficiary or the customer of that cellular networking service. Um, the immediate hop is the base station, and the base station operates as the bridge gateway between the wireless communication and the wired communication. So the base station is the one that takes the wireless communication and translates that to the wired communication. And of course, with multiple base stations, there's, a smaller number of core network, and the core network on the back end is connected with switches, to the base station. We're going to talk about different scenarios, like when the attacker is assuming the role of the user equipment, as well as when the attacker is the base station. Okay, so kind of going in this first scenario, we when we have an attacker that launches a denial of service attack. So denial of service is an attack against availability. It oftentimes involves flooding, but it's a type of an attack, that the attacker launches so that it occupies, let's say, a server, and that server cannot provide the service to other legitimate parties. But we look at such DOS based on wireless packet injection where the attacker is assuming the role of user equipment, and we do a detection of that threat. And we try to use these information features which are directly affected by the DOS attack. We also public publish our data set. We call that 5G NIDD. And that simulates these different kind of threats, based on DOS and based on attacking availability. So switching gears, and thinking about, the attacker that is assuming the role of the base station. So now the attacker is on the base station. We try to actually have user equipment that detects and blacklists such base station. And this research, yes, we do detection and blacklisting, which is the defense, but we also try to study the offensive side as well. And when we were studying the offensive side, we actually realized that the 4G, 5G, the current protocol implementation, is very fragile. So pretty much any deviation from the control communication in 4G, 5G can be utilized as a way for fake base station or malicious base station to DOS the channel. And that was pretty scary to us. So this is why we're starting to actually do our experimentation in a careful manner so that we don't accidentally affect the real phones that we currently have. Okay. So that's let me maybe pause here because I want to move forward and talk about post-quantum cryptography and see if there are any questions.
Uh, Hi,
Hi.
I'm Sang-Yoon. Thank you for allowing me to ask. So in terms of the machine learning, you mentioned about your methods that you use, for example, 5G and IDD work. I was just wondering how, if you could explain a little bit more details about how the machine learning was incorporated in that aspect of it. Thank you. Yeah, yeah.
That's a really good question. I so it's actually it's part of our future work. So we have the data set, and the data set is based on threat simulations as well as normal behavior. So we do have the data set. And the reason why we publish the data set and it's publicly out there is so that people can use this data set to use machine learning. Now, in this slide, with our current work, we haven't actually applied machine learning yet. The first bullet point over here is more like a statistical rule-based. So we actually thought of, how we can detect by ourselves as opposed to having the machine do it. Now, that future direction may look something like this. It may look something like, because we actually have these data set, and we know which scenarios have been used in each of the data set. So we know this is based on ICMP flooding, DOS attack. This is based on UDP flooding. This is based on slow rate. And these are like classical techniques in DOS. But then we also have normal traffic. So based on those, we can actually train the supervised learning model because they know it's the ground truth because we actually also simulate and implement the attacker. So those are ground truth, right? I mean, we're in a sense of attacking ourselves, right? We have one radio and another radio. This radio is attacking ourselves. So we have the ground truth. So we can actually have them as the labels for training. And then for testing, we can actually assume that we, after the training, after knowing what the ground truth is and how we can actually build the intelligence, we can actually try to test it afterward. Yeah, so that's probably a sketch of how we can
Yeah.
use such data for machine learning.
So just a follow-up, how do you get the original data to train your machine learning algorithm?
So so this is based on my collaborators from Holy University. But what we do is, and it's based on the SDRs, that I mentioned. I'm pretty sure that they also use USRP SDRs. So these SDRs, we actually have a test bed set up, and we actually have them communicate between the user equipment and the base station. So we set that up. And then based on that, we simulate a different user equipment, which is launching the attacks. Now, we are using open source software, but let me describe how close the open source software is against our current mobile network operator cell services. I'm talking about like AT&T, Verizon, Sprint, and so on. But the fake base station implementation that we have using these open source softwares, we can actually communicate with the user equipment. Now, we haven't tried taking the user equipment and communicating with the base station, not with the cell tower, but we did set up a base station and tried to communicate with our phones. And we actually saw, I'm holding my phones,
So
we actually
basically,
saw that it does communicate. Yeah.
yeah. So I'm sure you have some volunteers to offer this kind of you know approval to get the data from.
That's also a really good point. Here's what we did. At UCCS, we actually had a new building. It's called the Cyber Building. And we actually had it before. It's a new building distant from main campus. By drive, it takes 5 to 10 minutes. So there was this transition phase, when nobody was using the cyber building, the new building, and it's far away. And my dean even one time joked about I can do drone-based experimentation within that building. So nobody was there. So we did some of these experimentation while nobody was occupying it. We tested it with the phones that we have. So I purchased some phones, got some SIM cards, and then we tested it with our phones. But the moment that we realized that these open source software can impact our current phones, we started taking measures to limit the accidental harms that we can cause. Yeah.
Yeah, that's great. Yeah, that when you said there is a distance of about 10 minutes drive, immediately what I thought was about drones, and you're already talking about it. Yeah, that's great. Would you mind sharing the software? I mean, not the software programs, just the name of the program.
Oh yeah, absolutely. I So on the front end, we did use SRS-RAN. On the back end, we used Open5GS. SRS-RAN is primarily focused on the wireless communication between user equipment and base station. In cell networking, it's called the front end. Open5GS, involves the base station and the core network. It goes all the way to user equipment. But it does, like when people talk about network slicing or virtualization, then that's a little bit more on Open5GS. SRS-RAN is more on the front end. Yeah.
Yeah,
And these
sorry, I
are
didn't catch it earlier. Thank you.
Thank you for the questions. Yeah. And these are this is not like one lab that actually developed it. It's a pretty sizable effort, that made it. Yeah. All right. Well, thank you, Sammy, for those excellent questions again. So let's move forward and talk about post-quantum crypto. And maybe this is also a good time to talk about that HBO show Silicon Valley. So when I watched it, it has been more than 10 years ago, I think. When I watched it, it was a little bit of a letdown. It was a sad story because they had this startup, they had 6 seasons, and at the end, they just decided, to fail the launch and to discontinue with their startup company. And this screenshot on the right bottom corner is when Richard was trying to describe what their AI engine did. So it turns out that this frame is a gift from a friend celebrating the successful launch or the demonstration of the launch because they ended up not launching or not publishing it. And she was actually just showing the text message communication uh, uh, from Richard, right? And Richard, like he always like have these like 3 dots toward the end of his text, and he jokingly put 4 dots. And then he actually realized that his AI engine, because it was compression focused engine, it actually were able to break the end-to-end cryptography between his phone and her phone. So it turns out that he sent 4 dots and she sent 3 dots. And he talks about like how that's funny, and it was meant for a joke. But then there was a size difference, and then that's why they actually decided to scrap their AI engine and to discontinue with their startup company. And this was the end of the show Silicon Valley. Now, this is really important because it actually it's a good kind of episode to describe why cryptography is so important. Cryptography anchors our everyday digital security. So we have a bunch of applications. I'm pretty sure people here use phones, maybe online banking, but we rely on digital internet and digital security. And there are protocols, and within those protocols, there are these kind of building blocks called cryptographic functions or primitives. Now, I recently was watching or rewatching Bruce Schneier's video, and he actually also restated this notion of trust in math. So this is a very common saying because we have our current cryptography anchored with math. And more specifically, these problems that are known or assumed to be difficult to solve. And based on that, we have the crypto protections. Now, almost all of successful cryptography research and development, and I'm talking about, the cryptographers, all of the successful breaches or threats are largely based on, or they're successful threats on the implementation and the use. One example of that is this subfield or field called side channel. It's a big field. So far, the math have been robust. Now, so since the invention of the public key cryptography in the 1970s, thanks to Diffie and Hellman from Stanford, thanks to them, they have been robust. But now we're actually starting to see a crack in that. And the crack is being caused by quantum computing, or rather an attacker which can be equipped by quantum computing capabilities in the future. So assuming quantum computing, now we actually have a way called Shor's algorithm to break the math that anchors the cryptographic protection. This in computer science, they actually take a non-polynomial time complexity and then makes a polynomial time complexity. And as a result of that, and there are some proof of concept quantum computers. On the slide, I have the IBM quantum processor, but we do have quantum computers which support limited number of qubits. Qubits are different from digital bits, in the sense that they have superposition, and they're entangled, but they're based on quantum computing. Now, we do have prototypes of quantum computing, but the current quantum computing has limited qubits. And that's why at this time, we cannot actually take those quantum computers and break the existing math. They just don't have enough length for the bits. However, because we're starting to see quantum computing getting increasingly developed, where we as a community started working toward building cryptographic functions called post-quantum ciphers, which will be quantum safe, or which will be safe against quantum computers in the future. And NIST from US NIST, National Institute of Standardization and Technology, maybe, but NIST, which is a standardization government sector, is a big facilitator of establishing PQC ciphers. Now, NIST has been pretty important when it comes to cryptography. They are the ones which standardize, DES, data encryption standard, in the 70s, AES, advanced encryption standard, in the 1990s. But they always try to look at the future so that we can actually preemptively secure these ciphers and these crypto functions. So on this kind of timeline, and this is something that we drew, we're actually looking at the timeline of post-quantum or quantum safe technologies. And the black fonts are those that are outside of NIST, and the blue ones are the ones that are from NIST. And NIST actually had this, and it's still ongoing. We're on round 4, but they started in 2016, so it's getting close to a decade. And the way that they did it was they had a standardization. They called for ciphers, and then they had tens of ciphers in round 1. Then they get filtered out. Some get added in round 2, and so on. I guess the point here is that they went through a multi-year process and invited the cryptographers um, in the world to challenge or to crack those ciphers. So it's a pretty there's a lot of kind of effort. It's a global kind of open source, open community type of effort that NIST facilitated. We're currently in round 4, and in round 4, we actually did select some of these public key cryptography ciphers. There's one class called key encapsulation mechanism. There's another category called digital signatures. But we do have ciphers which got selected for standardization. So taking those ciphers, we actually tried to test the feasibility on different internet protocols, including DNSSEC, so domain name system security, PKI, which is public key infrastructure, QUIC protocol, which is the newer version or the next generation version of TCP/TLS, as well as transport layer security TLS. We had very positive results. The transition to post-quantum cipher are feasible, but there are also some challenges, that may affect the protocol design, including the data field sizes. And we actually think that the digital signature post-quantum ciphers would actually have a challenge in that regard, because these post-quantum ciphers, have very much longer length in terms of their digital signature and their public key sizes. But since I started kind of talking about cellular networking, let's shift gears, and talk about mobile computing and cellular networking. In cell networking, they do use cryptography, and more specifically, they also use public key cryptography. So this is Crypto 101, but there's public key cryptography and there's symmetric cryptography. Symmetric cryptography, quantum computing, as long as we increase the key length by double, we're okay. So it's not like taking non-polynomial time complexity and making it polynomial. But public key cryptography, we're more nervous, and that's why NIST is facilitating post-quantum ciphers for public key or asymmetric functions. When we focus on those asymmetric functions, we do have 5G using such asymmetric or public key cryptography for the protection of the mobile IDs, so the mobile user ID. And nobody wants, I don't want anybody to track, the whereabouts and which website I'm accessing using my phone. So it makes sense, the mobile privacy against phone tracking. It turns out that in cellular networking, they also use public cryptography for key establishment as well as authentication. And this is key establishment and authentication between the user equipment and the core network. I did want to clarify that because earlier I was focusing more on the wireless communication between user equipment and the base station, but these key establishment and authentication is from the user equipment all the way to the core network of the mobile network operators. So we actually test these post-quantum ciphers for these purposes. We tested, for that SUKI or the user ID protection, as well as also for the eSIM context, which is the bottom half. And we largely have very positive results. Here's what surprised us, because we call them pre-quantum, the current ciphers, public key ciphers that we use. You can think about RSA or ECDSA for digital signatures, elliptic curve based, the current ciphers versus the post-quantum ciphers. So my initial thought, I should speak for myself, but my initial thought was the post-quantum ciphers, because it has that additional security property, it has that additional security effectiveness, I thought it's going to be slower, and it's also newer, and generally newer, we expect it to cost more in terms of overheads and time and power. But we actually realized that those performances are very comparable, or sometimes even better. Um, so there is a trade-off in terms of making that transition from pre-quantum, the current ciphers that we have, to the post-quantum. The trade-off, it actually turns out that in terms of the time over it, how long it takes to apply those public key ciphers, is actually even shorter or comparable. So we actually consider this to be a positive win, and therefore the smiley face when we transition from pre-quantum to post-quantum. This particular plots, are in the context of 5G and for eSIM or embedded SIM. If you're traveling, then I actually recently started using eSIM maybe a couple of years ago, but I stopped kind of using the physical SIM because I don't, it's more convenient and to have eSIM as opposed to having that pin to open up that SIM chip slot. So the positive, we actually realized that time, power, and energy performance are comparable, similar, or even better. And power and energy are very important for these mobile devices. But the trade-off or the con, the negative, was actually in the payload size, as well as the packet size for transmissions. And this was because of the larger parameter size of the post-quantum cipher. The key size increased compared to pre-quantum. The digital signature size also increased compared to pre-quantum. So this actually makes just the message size larger when it comes to these communication protocol. So that's a con. And this is actually opening up some R&D possibilities, because we actually, when we talk about these very well-known internet protocols, as well as 4G, 5G protocol, they have the standardization and the regulation bodies are it's not like I like it takes some effort to make changes in those regards, and by some effort I'm talking about very sizable effort. So for post quantum I do see the necessity to change these protocols, which are oftentimes standardized by these standardization bodies and multiple organizations behind them. Okay, I do want to acknowledge the lab and the PhD students that I work with. Yeah, so here are the PhD students that I work with. The top row are the current students, and the bottom row are the graduates. I started having my second batch of graduates, and I'm very happy that they're launching their successful career. Okay, well, thank you very much for your attention. That's it for my presentation. I'd like to take any questions if you have any.
It's,
Dr. Lucas, yeah.
yeah, so I have a question if I could, I would be lying if I said that I followed all of the computer analysis here, but I got the sense that the post-quantum protocols is a new protection for our cryptography that will protect our systems. And as the World Affairs Council, I'm always thinking about what this means for international relations. And I know a big part of international relations now are different countries developing a capacity to break into our secure systems and threaten things like our infrastructure and our military systems and our security systems. And given the new developments you're talking about in terms of cryptography protections, how well will those be able to protect things like our infrastructure and our military from a foreign government that might want to attack those in sort of a as part of their foreign policy?
Thank you. Let me address that question maybe in two different perspectives. First is maybe the technical side of it.
Yeah.
The technical side, the NIST, they went through 10 years of facilitation. There has been a bunch of labs, academics, researchers, industrial researchers which have been trying to attack these ciphers. This is why I think they started off, maybe about like maybe 40 plus, cipher candidates in round one, and now we're in round four. The point here is the NIST actually did its due diligence in terms of trying to build these ciphers to be effective as much as possible, like robustness. And we do still have these. I mean, if history tells us, then these math, they really do not get broken that often, right? We're talking about public key ciphers, and the public key ciphers, thanks to Diffie-Hellman as well as the RSA the year after, but they got invented, in the 1970s. And those are I mean, we have adaptations and variations from it, but the math that we anchored back then has been sustaining us until now. So that really gives us some assurance or some confidence that these post-quantum ciphers will largely be. I have a chat that says I can't hear anything, but I'm assuming that you can't hear me. Okay, good, thank you. So that kind of speaks to the robustness and the effectiveness of these ciphers. Now, in cryptography, because I teach cryptography, we call these mathematical hardness assumption. These are assumptions. We don't have mathematical proof that they are difficult to solve. But we do try to have the community, the global community, come together to have a better sense of, where we stand for cracking these math.
I can't hear anything anymore.
Okay. Um, Dr. Lucas, I think you're muted.
Yeah, oh, Glenda, I was just saying the sound seems to be okay, so I think it might be a problem at your computer's end. Oh, I'm sorry.
It might help to turn off and turn on the speaker in your local device.
Should I proceed or just let me know when I can go ahead.
John, you're still
Oh,
muted.
yeah. Go ahead and proceed. I think your sound is okay. I think Glenda might be
Okay.
having problems with her speaker at her end, but I don't think we can fix that where we are.
Okay. So that was like the technical angle to it. Now, in terms of the use and the implementation, we still have systems that are using the legacy systems or legacy techniques. One good example may be the transition from IPv4 to IPv6. Nobody questions that we need IPv6. We're having more and more devices connected. 32 bits is not enough, but not many people believe that we can actually ditch IPv4 completely because we need that backward compatibility. So even though, and I think I think it was President Biden, but he had the presidential executive order to transition the critical infrastructure and the government to post-quantum. So there are really strong pushes to make that transition, but I think there's a big chance. I mean, I think there will still be the legacy systems which may be able to get exploited. So that is not necessarily, the design of these ciphers and the algorithms, but that's more on the lack of implementation and practice. But I do consider that to be, if between those two, I would actually consider that latter, the implementation and practice issue, to be a bigger issue.
Okay, thank you. So I'm a political scientist, so it sounds like the vulnerability is more on my end than on the technical computer end. All right,
We need
thank
more
you.
awareness. Yes.
Yes. Okay.
Yeah. We need more people to start, practicing post-quantum. Yeah.
I have one quick question. sorry, I don't mean to pry into your work, Dr. Chang. So these are based on mostly cellular communications you talked about earlier, in the range of gigahertz. I was just wondering if you had any thoughts or ideas or plans to work on in future, or maybe you tried earlier and then didn't find any use for it and gave it up in terms of megahertz frequencies.
For a moment, I thought you were gonna ask about, even tens of gigahertz, because in cell networking, I think the megahertz spectrum are being utilized. But in 6G, they call it millimeter wave. So these are tens of gigahertz. Now, earlier I kind of mentioned about many of the work that I do are based on implementation. And the implementation are facilitated by the software-defined radios or just the accessibility of these radio softwares. And that's making my students' lives easier. But these millimeter wave technologies, because when we talk about spectrum, I think the trend is to actually tackle higher and higher spectrum, like tens of gigahertz, which include the millimeter wave spectrum. Those hardwares are kind of harder to get than the ones that actually work in the gigahertz range.
Yeah.
So I'm not sure if that answered the question.
Yeah, I understand that. So I was curious about it because that's mostly used in the near field communication. So how much preference you give to research in that area? That was my curiosity.
Yeah.
Nothing else. Thank you.
Yeah, I think I come from like a cybersecurity angle. Well, I think I mentioned that earlier in my career, in my student career, I was also working on communication signal processing. But when it comes to cell networking, they really do a good job in terms of these communications. We actually have these cell towers now being able to serve, multiple phones, like massive MIMO. But when it comes to security, I do think that they are significantly less developed. Yeah. And I think I was trying to hint on Wi-Fi versus cell networking, because Wi-Fi, they work or they operate on unlicensed band. Whereas, cell networking, they operate based on licensed band. I think maybe like a decade ago, Google was trying to buy a spectrum. They were not able to because we had like Verizon, Sprint, which had existing relationships. And they were the ones who actually got those spectrum. Yeah.
Thank you.
Okay.
Well, Professor Chang, I think on that, I would like to thank you for a great talk, and it was an incredible privilege for us to hear from somebody who's right at the cutting edge of the research in this and hear about where we are. And so, on behalf of all of us and the World Affairs Council, I would like to thank you for a great talk and have a great evening.
Thank you, Dr. Lucas. Thank you for your questions, Sammy. Everybody, it was a pleasure. Thank you, everybody. Have a good evening.
Yeah, thank you. And thank you for coming, everyone.